Welcome back, everybody. Apologies. I have immense allergies during this time of the year, and so I probably look like death, and I'm feeling a little fuzzy because of it. But we'll get through this. With regards to the homework, I had forgotten to do it, but I have done it this morning. I've extended the 3.2 homework until this coming Sunday, and then also with 3.1, I was debating whether or not to remove the topics on one-to-one functions or to give full credit. I opted for trying to give full credit, but that didn't seem to work out because there was no way to give individual credit for certain topics. So I just ended up giving everyone tens on that section. So that's my workaround. Um, I intend to do everything in my power to have your exams back, you guys, on Wednesday. And the other thing that's on the pipeline, because I am worried that we will not have enough time to fully digest all the topics in time for Monday's exam three. I am moving it to the exam to Wednesday of that week. So not Monday of next week, but Wednesday of next week is when we'll have our exam three. If this affects your schedule in any way, like if you have an exam in your physics class that is on the same day and you were planning on doing something like that, just let me know and we can work something out on that front. But yes, the exam three has been moved to Wednesday. Okay. And if I am able to do everything in my power to get them to you on Wednesday, that would mean that your exam redos for exam two would be due on Wednesday, which is the day of the exam. So we'll just extend it until Monday. So, anyways, any questions before we get started?
Well,
Yes.
is there a way on Alex to practice certain sections?
Yes.
Okay, is it the learn button?
So it's not the learn button. There's a button on Alex that says if you click on that little hamburger menu at the top, one of the things that is an available option is review. And if you click on that, it'll go to it and it'll just randomly generate one of the topics that you can review. Typically, if memory serves, it's one of the most recent ones that you've done. But when you're on that page, there's a little, as you see on Alex, there's always like a little menu at the top, and there's a little drop down bar with a little arrow, I think it's what it looks like. If you click down on that arrow, you should be able to go to a section where you can choose which section you want to go over. So if you want a question specifically from Unit 1, you can go to the Unit 1 section and click for those things. And then once you've chosen like 1.1, it'll populate with all the different topics from that section. Is that okay? Yes, excellent question. Any other questions? Okay, so exponential functions, which is going to seem like a left turn from what we were doing. We were talking about inverse functions. Why are we talking about exponential functions? Well, they have a close relationship to something new. We needed inverse functions for 3.3, and 3.3 is only possible if we know what 3.2 is. So anyways, you probably have seen them before in your lifetime. They're very, very common. They're probably one of the most useful applications in all of mathematics is the concept of exponential growth. An exponential function is, of course, a function because it's a function, but and it's a function of the form f of x equals b to the x, where b needs to be strictly greater than 0 and b should equal 1. And we call that number, that value b, we call that the base of the exponential function. Now, if you're wondering why b needs to be strictly greater than 0, it's because otherwise we end up trying to take square roots of negative numbers. So you don't need to write this down, but just imagine if we had the function f of x equals negative 1/2 to the x, negative 1/2 to the x. Well, let's do actually negative 4. Negative 1/2, negative 4 doesn't matter. If I try and take this function, it works for certain numbers. If I plug in negative 1, I get negative 4 to the negative 1, which is negative 1/4. If I plug in 2, I get positive 16. It's all fine. But if I try and do something like f of 1/2, That's -4 to the 1/2 power. But as this rule above states, the power goes above and the root goes below. So this is the square root of -4, which is not a real number. And we're not interested in functions that are complex in this course. So that is the reason why the base needs to be strictly positive. And the reason why it shouldn't be 1 is then you have the what we call the trivial exponential function. 1 to the x, if your base is 1, you have this, but 1 to any power is just 1. So it's not an exponential function. It doesn't grow infinitely. It just stays constant. So anyways, that is the reason for these two suppositions about the definition. We're to graph these two functions, f of x equals 2 to the x and g of x equals 1/2 to the x by completing the tables to plot them. So those are two exponential functions. F has base 2 and g has base 1/2. So I've already started to plug in some values for f of x, which I'm going to highlight in blue. Not that it really matters. You can draw them both in pencil if you'd like. But if you plug in -2 into the function, that's 2 to the -2, which is really 1 over 2 squared, which is 1/4. So you have the point -2 comma 1/4. If you plug in -1, you get the point 1/2. So we have the point -1 comma positive 1/2. If you plug in 0, you're going to get 2 to the 0, which is 1. So you have the point 0, 1. Then you'll get 2 to the first power, which is 2. So we got 1 comma 2. And then if you plug in 2, you get 4. So you get 2 comma 4. Now on the flip side, with 1/2, if you plug in -2 into g, you've got 1 over 1/2 to the second power. That's 1 over 1/4, which is positive 4. Thank you. You're probably going to be saying that a lot today with these allergies. If you do it again, if you do -1, by the similar logic, you get 2. So we have the point -1 comma positive 2. At 0, we will get 1. So we have the point 0 comma 1. If you plug in 1, you get 1/2. So we have the point 1 comma 1/2. And then if you plug in 2, you get 1/4 because it's 1/2 squared, which is 1 over 2 squared, which is 1/4. So 2 comma 1/4. So there's this interesting duality between these two bases. These two bases are multiplicative inverses of each other, right? 2 and 1/2, they multiply to 1. And they end up having flip-flopped answers. Flip-flopped y values, excuse me. Oh, and let's graph this one in red. So if we take all those points that we've got, let's plot the blue curve first, 2 to the x, and add the point -2 comma 1/4, which is right about there, then -1 comma 1/2, then 0 comma 1, 1 comma 2, and 2 comma 4. Now you can continue on this process to find, like, this thing is going down, but how much does it go down? Does it go like this, like that? How does it look? And the fact of the matter is, let's look at some other numbers. If you plug in -3, you get 1/8. -4, you get 1/16. -5, you get 1/32. They're always positive numbers, but they're just getting closer and closer and closer to 0. So in fact, this curve and 2 to the x for the same reasoning has a horizontal asymptote at y equals 0. HA at y equals 0. So what these curves end up looking like is something like this. That's the y equals 2 to the x. And on the flip side, with the red curve, you had -2 comma 4, -1 comma positive 2, 0 comma 1, 1 comma 1/2, and 2 comma 1/4. So it looks like the mirror image. One might even say a reflection across the y-axis. Do you remember those ones? So a reflection, remember there were two different types of reflections. If you had a function y equals f of x, then there was negative f of x, and there was f of negative x, right? Which one was the reflection across the y-axis? 1 or 2? 2. It was 2 because this one changes the y value because it's on the outside. So that would like the negative, the x-axis reflection would take the y value and flip it down here. But this one is a reflection across the y-axis. And so it's f of negative x. And that makes sense just as a fun little algebra trick. If I took f of negative x, you don't need to write this down. That's going to be equal to 2 to the negative x, but that's equal to 2 to the negative 1 to the x. Right? Because power raised to a power means you multiply the power. So I can work backwards. I can also split apart a product of things into power raised to a power. And 2 to the negative 1 is 1/2. Just goes to show you that these two functions are they are reflections of each other because it is in fact, you can show the work to show that it is in fact the reflection. So if you reflect y equals 2 to the x across the y-axis, you end up with g, is what I'm trying to say. Anyways, moving on to the properties of functions. So first and foremost, the domain of an exponential function is all real numbers. This is one where I think that it is important to actually make a distinction, whereas in 2.1, when we were talking about quadratic functions, it always had that question, it was like, what's the domain of this quadratic function? It's always negative infinity to positive infinity, and it seems like a hoop jumping. It's going to be a hoop jump here as well. However, it's important to understand that exponential functions are defined everywhere. They can take any number and they spit out a number. They are well defined. They're some of the nicest curves out there. And their range is 0 to positive infinity, not including 0. Now, that is a big deal. And it's something that gets brought up many, many, many times throughout your mathematical career. It's something that is working always in the background. If you plan on taking calculus, you're going to need to use that fact. You're going to need to use that fact a couple times. So the reason why I think this is a big deal is this means b to the x is strictly greater than 0 for all x. Thus, b to the x never equals 0 for any x. This is a very important point about exponential functions. An exponential function by itself, e to the x, b to the 5 to the x, 2 to the x, 1/2 to the x, they are always strictly positive, and they are never 0. So if you have an equation and it's equal to 0 and it's got an exponential function, the exponential function doesn't give you anything. You'll see that occasionally, especially in calculus. Then they have 3 important points. Alex usually only needs you to have 2, but I like to give the third one, is that f of 0 for any exponential function, b to the 0 is always equal to 1. Then f of 1 is equal to b to the first power, which is just b, and then -1, that's 1 over b. So this gives us the 3 following points. We have the point 0, 1, 1, b, and -1, 1 over b. These are points for graphing. You guessed it, transformations. Who loves transformations of functions, right? It's all of our favorite section. Math unit 1.6. Everyone's favorite part about unit 1, right? Good, good. So it comes back, and it's just a good practice. Think of it this way. This is just more practice getting you ready for the final exam. Because I can't say for certain, as a reminder, the final exam is departmental. It's cumulative and departmental, and I have no say over what goes on it. So they could put a linear transformation problem on there. I would suspect that they would. I wouldn't be surprised to see at least one on the final. So this is just free practice. And then last but not least is that they have that horizontal asymptote at y equals 0. So if there is one thing I want you to remember about exponential functions for the rest of your life, if there's one thing I can just make sure that you know, it's that exponential functions are always strictly positive. An exponential value is always positive. B to the x will always be greater than 0. The graph of b to the x will vary based on the value of b. If your b value is greater than 1, like 2 to the x, or 5 to the x, or 6 to the x, it will look like this. It will start very, very small on the left, and it'll shoot up, and it'll start growing very, very fast right after 1. It starts to grow incredibly fast after, pretty much after 0, but especially after 1. And then if your b value is between 0 and 1, then this is what your graph looks like. So it's like we're thinking about like fractions, like 1/2 to the x, or 2/3 to the x, or 1/5 to the x. But they like no matter what shape it makes, it always still has that that horizontal asymptote at y equals 0. And we get to talk about the natural base. Unless there's any questions on any of those properties about exponential functions. E, my favorite number. E is a fascinating number. So E is from now on, from the rest for the remainder of your mathematical career. If you see E in an equation, it is not a variable. It's a number, just like pi is a number, right? And the reason why we have to write it as with a symbol instead of writing it out as a number that we know and love, the problem is it's an irrational number, which means that it goes on forever. You could never write out all the digits of E, just like you can't write out all the digits of pi. So it is written as an E, and it is approximately 2.72. Um, just like pi is approximately 3.14, E is approximately 2.71 or 2.72. Your call. And it is the reason why it's called E is named after the Swiss mathematician Leonhard Euler. So I know it looks like Euler, but it's pronounced Euler. Very, very influential mathematician, probably one of the most important in all of mathematics. And E is one of the most unique numbers in the history of mathematics. This is one situation that we can understand right now based on our limited knowledge about the arrow symbol's meaning. So what that means is that as n goes to infinity, you get an infinite you get that this value approximates E. In fact, 1 plus 1 over 1 plus a over n to the n approaches E to the a, which is interesting. Um, if you like, and that might not seem like a big deal, but we can actually talk about this here. I'm going to be bringing this up with my calc students, but that's a big deal in mathematics if you don't even realize it. So there's a fact in mathematics that if I take any finite number of rational numbers at any finite number of fractions and I multiply them together, I always get a fraction, right? 1/3 times 1/4 is 1/12. 2/3 times 1/5 is 2/15. They always end up making fractions. And I can do this infinitely many times, like finitely many times. Even if I have 2 billion to the 2 billionth terms, when I multiply them all out, as long as it takes me, it'll always be a fraction. So a rational number. But for whatever reason, so what this is right here, for any specific n value, it's just a bunch of fractions being multiplied together, right? If n is equal to 2, that's going to be it's going to be 3/2 squared, because it'll be 1 plus 1/2 to the second power. That's 9/4. It's a number, it's a rational number. But for whatever reason, when I make it go to infinity, instead of being a finite number of multiplications, if I make it an infinite number of multiplications, it goes from being a rational number to an irrational number. And I feel like that says something very, very unique about the universe, if you think about it, right? It takes the concept of infinity to create an irrational number. which is very, very strange. So I hope that kind of makes you a little bit piqued into the interest about mathematics and infinity. That is what calculus is at the end of the day, if you want to know. Calculus is the study of zero and the study of infinity. That's basically what it is at its core. Anyways, we call E the natural base, and it's because it shows up so frequently in mathematics, and in life more than you realize. Um, and if you plan on taking chemistry, or if you are taking chemistry, you've probably heard of the half-life formula or the doubling formula if you take biology, and they usually write them as 1/2 to the x in some textbooks. That's wrong, in my opinion. It really should be e to the x because there's something that we can prove. We're not going to do it. It takes a little too long. But every exponential function can be converted into a natural base, which is pretty cool. But anyways, uh, the point being that this is what I want to write in this thing. The point E is just a number and y equals e to the x is an exponential function like the others. That's the point. So you will have to graph e to the x. You will have to graph random bases other than the natural base. But e is the coolest one. Everyone's always up in atoms about Pi Day. Oh, it's March 14th. Yay, 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 Pi Day. E Day is way cooler. We don't celebrate the 7th of February nearly often enough, but one day we will. It's such a cooler number. There are many, many useful facts about it. But either way, that take calculus, by the way, to truly understand why that function is so cool. But anyways, the key point that I've got some graphs of different exponential functions with different bases. And the thing I want you to kind of realize is that the larger the base, the faster it's spot like the steeper the graph. The larger the base, the steeper the graph. And so notice that e to the x is sandwiched between 5 to the x, 5 to the x and 2 to the x. It's sandwiched between those two things because e is approximately 2.71 or 2.72. So it grows faster than 2 to the x, but slower than 5 to the x. Okay. So once again, the reason why I brought up the three important points is because now we will need to be able to graph them. So you can either look at these as linear transformations, which will help you in the grand scheme of things, potentially on a final exam. Once again, I can't confirm the existence of one of a linear transformation problem, but I've seen it happen in the past. I've taught Math 126 and 126E most semesters that I've been teaching at CSN because I love this class. And most years there's at least one. So it would be a good idea to not just try and do it the fast way, but instead do it the long way so you get more practice. But I'll show you the quick way in case you're curious. So first and foremost, its parent graph is y equals 2 to the x. And so that function has the points 0, 1, 1, 2, and -1, 1/2 with a horizontal asymptote at y equals 0. This is here so that we can follow the transformations throughout. Specifically, we're going to try and Alex only requires 2 points on these ones. So we're going to avoid the one that has the fraction. So in this case, this 2 to the x has the point -1, 1/2. But if I try and move that around, it's going to be hard to follow it, as you'll see, but we'll still do it. So anyways, There is no negative x in this, right? There's no negative x. So we skip that step in my procedure of how to do transformations and go straight to RCS. So no negative x, skip step 0. I can't remember if it's step 0 or step 1, but maybe we just say skip initial step. Are there any reflections? No, because there's no negative x and there's no negative in front of the function. So NA or none, your call. Compressions or stretches. That would be multiplication on the outside or on the inside. So if there was a 3 here, so like a 3 times 2 to the x, like that would be a vertical stretch by a factor of 3. Or if it was 2, like right here, let's erase it for just a quick second and write, if it was x over 3, that would be a horizontal stretch by a factor of 3. But there is none. So there's no compressions or stretches. So we write NA. But there is a shift. Is this shift is it vertical or horizontal? Vertical, because it is happening on the outside. The inside of this function is right here in the exponent. For an exponential function, the inside is the exponent. So if this was instead, if it was like this, that would be a shift right by 4 because that's on the inside of the function. But this minus 4 is on the outside. And if you're ever uncertain, this is a problem in mathematics. It's kind of hard to see sometimes. So if you're ever uncertain on an exam or on the final, you can always ask for clarification, and I'm happy to clarify. But either way, so this is a shift down 4. So now that we have all of our one transformation taken care of, and we have our 3 points, let's go ahead and work with them to plot them. So we had the point 1 comma 2. It doesn't get reflected. It doesn't get compressed or stretched. It goes down 4. So 1, 2, 3, 4 to the point 2 comma negative 2. So I'm just going to jot that down off on the side. You can plot it if you want, but I always just recommend not doing that just in case it gets the graph muddy at first. Then we have the point 0 comma 1, and it just gets shifted down 4 units. 1, 2, 3, 4 to the point 0 comma negative 3. And so when you're working on Alex, those are nice integer points. Every single time we move to a nice new integer, whereas that's not going to be the case with this one, right? Negative 1 comma 1 half, shifting it down 1 unit brings it down to negative 1 half, then negative 3 halves, then negative 4, negative 5 halves, and then negative 7 halves, right? So trying to do that in your head with your little pencil feature on Alex would be unideal. That's why they give you just 2 points is enough. But I wanted to plot that one, and so you can kind of the good news about using your hand instead of having to do it on an Alex program is that you can write your approximation, right? This going down 1, 2, 3, 4 to negative 3.5. Negative 1 comma negative 3.5. So let's plot those points. Negative 1 comma negative 3.5, 0 comma 3, and negative 2 comma negative 2. Okay. So if I were to graph that, where is its horizontal asymptote? Now at y equals negative 4. So this brings up a very, very good point to mention in just a second. But yes, you can continue doing, like, if you want to verify it, take the next point, negative 2 comma negative 1/4. If you bring that down, you'll get negative 3.75. And then you'll get negative 3.8725, I think. Yeah, 3.8725. And then so on and so forth. And they just keep getting closer and closer and closer to -4, but never actually reaching it. But all we need for the graph is to plot our, like for on Alex, all you need to do is plot your horizontal asymptote and 2 points. So use the integer points. And with that in mind, we can then graph this curve as best as we can. So looking at it, the domain is the hoop jumping problem. It's all real numbers. But just as a reminder, that what that's telling us, which is important to understanding of domains and stuff, is that exponential functions are defined everywhere. It doesn't matter what the number is on the inside of the exponential function, it always exists. The range on this one, remember we start at the bottom and work our way up. So the first y value that we can look at is -4, but this is a horizontal asymptote that it never crosses over. So -4 can't be included, but everything after -4, above -4 is included. And its horizontal asymptote is y equals -4. So the point is that HA travels with the vertical shifts. That's the key thing. So you can, like, if you're ever uncertain when you're doing those ones, just look for the number that is involved with the vertical shift, and that will be your horizontal asymptote. And it's because if you're trying, like, what a horizontal asymptote is doing is it's trying to figure out the end behavior, right? And as x goes to -infinity, as we go infinitely far to the left, our y values tend towards 0. So what that's telling you is that as you plug in more and more negative numbers into the 2 to the x, they become closer and closer and closer to 0, leading us to just having -4 being the horizontal asymptote. But either way, and it kind of makes sense visually as well. If I take this curve and I move it left or right, it doesn't change where the horizontal asymptote is. If I were to stretch it, yeah, the curve would get stretched, but its horizontal asymptote is on y equals 0. So it doesn't have a magnitude at all. So anyways, doing this one. Unless there's any questions on that one, that previous one. Okay. So this one here, 5 plus 1/3 to the x. So this one, let's just rewrite it in the way that it looks better. So that's 1/3 to the x plus 5. So much like before, there's no no reflections at all. There's no compressions or stretches. There's just a shift up 5 units. RCS, NA, NA, and NA. Its domain will be -infinity to +infinity. That's guaranteed. And its range, let's try and figure it out without graphing it. It's going to get shifted up 5 units. So that means that its horizontal asymptote at y equals 0 will get shifted up 5 units, meaning that its horizontal asymptote is y equals 5, and its range is therefore 5 to +infinity because of the way this function works. Now, this function has the points, like the parent function, that is. Just as an aside, you notice that I didn't give us a parent graph little spot. But the parent graph has the points -1, 3, 0, 1, and 1, 1/3. So if you want to do this based purely on graphing transformations, you're going to pick these 2 points and shift those things up 5 units and call it good. That being said, if you don't want to do that, you can always plug in numbers. You can plug in random x values and see what you get. And Alex will allow you to plug in fractions. Just make sure you don't do approximations of the fractions. If you write 1.33 instead of 1/3, it will mark it wrong. It won't plot the right point because 1/3 is 0.3 repeating. So, anyways. We have the point -1, 3. And we're going to shift that up 5 units. 1, 2, 3, 4, 5. So that point goes to -1, comma 8. The point 0, comma 1 gets shifted up 5 units. 1, 2, 3, 4, 5 to 0, comma 6. And as we said, there's going to be a horizontal asymptote at y equals 5. So with that in mind, we can then graph the curve. This is one that has the base that is between 0 and 1, so it makes the opposite shape. As x goes to infinity this time, instead of negative infinity, as x goes to positive infinity, further and further to the right, that's when it levels off at 5. Any questions on that?
If if the function is f of -x, it would reflect across the horizontal asymptote, right?
Yeah, it would reflect across the y-axis. Yeah.
So if it's negative f of x, then that would reflect across the asymptote.
Yeah, that would make it reflect there, right? Yes. But the asymptote would still be based on the vertical shift. Yes. All right. This last one, in the interest of time, I'm going to have you guys figure it out for yourselves. But what I will tell you is that it ends up looking like this. Something like that. Okay? It should look something like that at the end of the day. Let's graph an e to the x one as well. So this one, on Alex, you're going to need to use that plot pointing feature, point plotting feature, that thing that looks like this. It's like in the grid or whatever. And when you're in that feature, there will be a button to use powers of E. So that's going to be kind of the best way to do this. Some of them, there is like a thing where you can like, one of the problems, if I remember correctly, it does have like that feature we got in 1.6 where it's like, here's the graph of E to the X, use the translation feature and the up and down feature and the stretching feature. It should have that one, but otherwise you can just plug in the points, like plug in X equals 1, as we'll see here in a second. So if I do f of, let's do f of -1. And that's going to give me 2e to the first power -3, which is 2.437 approximately. So we're writing the approximation for our caveman hands to draw these things, but on Alex, when you're plugging in this point, you would plug into the point -1, 2e minus 3. That's what you would write. And it would plot that point for you. So there's a button that says like there's a button on the side when you get into that window. It's like it gives you 2 boxes. And then over here, there's like a fraction button, there's an E button, and there's something else I can't remember. So you want to write the exact form. -1 for your x input, your function value, your output is 2e minus 3. But because we're graphing this ourselves, we need to know exactly where to plot it. So that's basically 2.5, a little less than 2.5. So at -1, it was 2.4, right about there. And what you'll notice, if we do f of 1, f of 0, it's going to put us outside of the map, out of the graphing grid. So if you start going too far outside, just keep moving further and further left with your x values until you get something that works. I'll do f of -2, and I get 2e to the 0 minus 3, which is -1. This is the one time that we get a nice integer number, because you get e to the 0, and any base raised to the 0 is equal to 1. So -2 comma -1. Where does this curve have a horizontal asymptote? Y equals -3, because this thing gets shifted down 3 units. So we have a horizontal asymptote at y equals 3, and this allows us to figure out the rest of the shape of the graph. This thing has a base of e, which is a number larger than 1, so this thing should start low on the left and then blow up on the right. So it should look roughly like this. Exactly how far up it goes is hard to tell without more points. But if you plug in 0 into the function, you end up getting like 11.7. So that's already off the charts. So that's what it looks like. Now that we have that, we didn't need the graph to figure out the domain. The domain was -infinity to +infinity. But the range, if we could figure it out without graphing, but we could figure out without graphing, but we don't have to. We have the graph, so we can now figure it out. It's going to be parenthesis 3 to +infinity. All right. And then I'm going to skip this other one and suffice it to say it will look something like this. There will be an asymptote that is not y equals 0, and it will look like that. Despite it having a base that is positive, like or greater than 1, right? The greater than ones, they're supposed to start off and go up, but the problem is this one has been reflected across the x-axis, the y-axis. Okay. So right now we're going to start a little bit of the applications of exponential functions, but it is not the full extent. So the two most common applications of exponential functions, one of which is exponential, compound interest. So the compound interest formula, which is how you calculate interest on a bank, on a savings account, pretty much, not on an IRA or a retirement account. Those things use a formula called the amortization formula. And then there's the different types of like Roth versus non-Roth IRA, where tax is taken out before or after the money is received. But regardless, the formula for a savings account is A equals capital P times 1 plus R divided by N raised to the NT. Where a lot of textbooks will call it the future, the total amount. And I never really liked that terminology because, like, is that the total amount in the account that I put in initially, or is that the total amount in the account after the problem's done? So it always confused me. So I am calling it the total amount or the future amount. It's going to be the amount that is present once the loan or the banking appreciation term is up. P is called the principal or the initial amount. Most people call it the principal, but I prefer to call it the initial amount. R is the APR, the annual percentage rate, as a decimal. You will find out that your numbers get increasingly large if you do not do that. So if it's 7%, that's 0.07. If it's 1%, that's 0.01. If it's 0.1%, 0.5%, that's 0.005. So all you need to do is just move the decimal place 2 units to the left to convert it to decimal form. And that is the n is the number of times it is compounded per year. So monthly would mean 12 times per year. Weekly would mean 52. Daily, I believe there's a rule set in, but not in our course. But for computations in finance, I believe it's 360. You ignore 5 days or something like that for a nice round number. And then T is measured in years. The continuously compounded interest formula, which is the the formula, if you were to be able to compound it at every instant of time, which never happens. If anybody finds an account that gives continuously compounded interest, please let me know. I've never seen it. I've never seen it. So I don't even know why we teach it. Both like not just in this class. This class it kind of makes sense because it's an application of E, sure. But like even in finance classes, when I was teaching business algebra, we taught it. And I've never seen an account use continuously compounded interest. So please let me know if you find one. But what it is A equals P times E to the RT. So there is no N in this formula. And E is exactly what you think it is. It's 2.72-ish. It's the irrational number. And so the reason why N isn't there is because in this case, N is infinity. It's compounded at every instance of time possible. But that never happens. RT. Yes. That is the most common use of it. And then you have the other two more common ones, exponential growth and or decay, which a lot of textbooks have their own versions of it. The way I like to represent it is y equals y sub 0 e to the RT, where y is the amount. Like if we're talking about exponential growth, maybe it's like exponential growth of a population of bunnies or wolves or something like that. Then y is measured in the number of wolves present or whatever it is. Y sub 0 is the initial amount, or y, sometimes called y naught. R is the relative rate in decimal form. And then an additional note about this is if R is strictly greater than 0, it's growth. And if R is less than 0, it's decay. If you have a positive R value, that means that the function's going to go increasing as you go to the right. So it's going to be growing as time goes on. Whereas if R is less than 0, then that ends up making it decay over time. And then T is time, but it's not measured in years because this is a very, very overarching theme. You could be talking about the population of bacteria, which multiply very, very frequently, like we're talking once every couple of minutes or seconds. Whereas it could also be like human populations, which take much longer to grow because it takes roughly 9 months to grow a human. So, and then population growth, which is a very, very special subset of exponential growth and decay, is P is equal to P sub 0 times 1 plus R raised to the T. This isn't the case where you know the exact rate at which the population is increasing by every year. And we'll see an example of that. And then R is the rate of increase in decimal form. And I know that that's annoying. You have to write it 3 times, but it's because I want it to be very, very clear that you cannot, like, you should reflect on your work on these problems. And you'll see that if you use the non-decimal form, your answers become obscenely large. So it's a good technique in making sure you question your work. And the one I'll quote to is when I teach Math 120, one of the things that you go over in Math 120 is you go over finance math and you go over mortgages. And the mortgage formula is more complicated than this, but it still involves the whole thing of converting the APR to a decimal format. And if you don't, you have what happens to my students sometimes where I say, like, how much would your monthly payment be on a $400,000 house at an APR of 4% on a 30-year loan? And their answer is $32. And if you can get it for $32, you just keep that on lockdown. You don't mention that to anybody. Someone at Fannie Mae is going to get fired. But that's not your fault. They made the mistake. So make it convert to a decimal. So for example, Isaac invests $3,500 into a savings account at a rate of 8.3% compounded annually. Assuming that no withdrawals are made, so it's more like a CD than just a savings account. Find the total amount after 3 years. Also, how much more would the savings account make if it was compounded continuously instead? So it says compounded annually, and it also says compounded continuously. That means we're dealing with the formulas. A equals P times 1 plus R divided by N raised to the NT, and A equals P e to the RT. The good news is that both of them share the exact same letters. A is still the total amount or future amount. P is still the principal amount. R is still the annual percentage rate, and T is still time. So let's identify everything that we know and everything that we don't know. So, do we know A? Nope, we don't. Because A is the future amount. It's the amount that we want to know about. And we want to know the total amount after 13 years. So A is unknown. P, the principal or initial amount, is 3,500. R is 8.3%, which is it's 8.3%, which we convert to decimal form 0.0083. Oh, no, 0.083. 0.083. Sorry. You just move, like another way to do it is a percent. By the way, in case you did not know this, the reason why it's called a percent, cent in Latin means 100. That's why a centimeter, there are 100 centimeters in 1 meter. So percent means per 100. So 8.3 per 100, 8.3 divided by 100 is 0.083. And last but not least is time, which is 13 years. So compounded annually. That means that n is equal to 1. If you're compounded annually, that means you're compounded once per year. If it said compounded quarterly, that would be 4 times per year. So that's going to be A equals P, which is 3,500, times 1 plus R, which is 0.083, divided by N, which is 1, raised to the 1 times 13. And if I plug that into my calculator, I get approximately dollar signs, $9,868.20. So we're gonna round to the nearest hundredth because that makes sense. But because dollars and cents, right? But it also makes sense. Okay, good. I'm glad I explained it more. That makes it funnier. But anyways, so that's not bad. It basically tripled in size. Just a little less than tripled in size, but it did take 13 years. I mean, that's like 5 PS5s that I could have bought, right? There's 7 PS5s that I could have bought in 13 years' time. So like weigh the amount that it takes. Like that's not a very good thing. And plus, you're never going to see an 8.3% interest rate. I'm sorry to say it. If you can find a bank account or or credit union that gives you an 8.3% return rate, never leave. That's an amazing return rate. So I would keep that. By the way, so that was compounded annually. If you didn't convert 8.3 to 0.083, the amount that would be in the account would be 1.36 times 10 to the 16th. That's over $1 trillion. So that is a pipe dream. That'd be great, like somebody at Wells Fargo or Bank of America is now gonna lose their job, but you're gonna be rich, be up there with the top richest people in the world. Anyways, so that's why you want to question your work as you go along with this. If the number seems too outlandish, it probably is. Then versus compounded continuously. That's going to be A is equal to 3,500 e to the 0.083 times 13. There's no n value here. It's just A equals P to the times E to the RT. And if you plug that into your calculator, you get approximately $10,296.08. So John Doe student boxes these two things as their answer. Why is John Doe student going to get marked off 1 point? Yes. The question was, how much will be in the account after 13 years if it's compounded annually? And the second part of the problem was saying, how much more would they make if it was compounded continuously? So this is not the right box. What we want to do is take $10,296.08 and subtract off $9,868.20. And so it equals $427.88 more. The reason I bring this up at all is to bring you to the observation that the more times that interest is compounded, the larger the yield. So in practice, if you are borrowing money, you want it to be, of most importance, the annual percentage rate is the biggest hurdle. That is the thing you always want lowest if you are trying to borrow money, highest if you're wanting to receive money, like in a bank account, like a savings account. But the more times it gets compounded, the more money that gets accumulated, whether that be good or bad, depending on if it's a loan or a savings. But anyways, any questions on that? Nothing? Okay. And then this one, the delightful town of Orgrimmar, totally random name, not from any fantasy world at all. Regardless, the delightful town of Orgrimmar has a population of 32,180 people, or humanoids, and it is growing at a rate of 2.65% per year. If this rate continues, how many people will live in Orgrimmar in 5 years? So this is a population model because it's talking about a population and they give you the raw percentage that it is increasing by over time. So we are using P is equal to P sub 0 times 1 plus R raised to the T. Now, P sub 0 is known, 32,180. R is known. It's 2.65%, which we're going to convert to a decimal by dividing by 100 and do 0.0265. And the time measurement is in 5 years. So that's all we need to use. We've got everything we need. We just plug it into the formula. P will equal 32,180 times 1 plus 0.0265 raised to the 5th power, which is approximately, it's going to equal 36,675.9024, and we're going to round to the nearest person. 36,676 people or orcs. That's what you'll have to write on Alex. right? Because it wants you to round to the nearest whole number if you're talking about a population. However, I have had cheeky students in the past write what is 90% of 40 weeks? What is 90% of 40 weeks? $36. So you could also answer it, and I would love this on the exam if this is the problem shows up. 36,675 people with one person who is in their third trimester. That would be a great joke. I mean, it would definitely make the grading of the final exams a little bit easier for me. So, anyways, last one, which I'm gonna skip for now, but I'm gonna get it set up for you. It's an exponential decay problem because it's talking about a radioactive substance that is decreasing in size. So the fact that it's saying that it's a continuous decay model means that we are using y equals y sub 0 e to the RT, and R will be negative. So it says that the relative rate is 11% per hour. This right here means that R is equal to negative 0.11 because it's a decay rate. So this is the problem with English versus mathematics, right? When you're converting English to mathematics, the context is saying that this is a decay problem. So the R value, even though it says that a rate at 11%, it means a negative 0.11. And the answer that you should get for this problem is 2,995.69 grams. That's what you will get. So please do that one a little later today. Just give yourself some practice. Do not fret about those equations. You will be provided all of them. If they show up on the exam for whatever reason, they will be provided. So if there's a compound interest problem, the compound interest formula will be provided. And that's basically what we can do with them right now. We're going to learn some things as we continue on in this unit that allow us to have some more fun with it. But until then, we'll go ahead and call it good there. Let's go ahead and take our break. Let's come back at 107. It's like a 5 minute because we got to get we got to make some headway. And then we'll get back into it. People watch the recording, go take a breather, and then come back. Okay, so we're back, and now we're going to talk about the next type of thing. So, why do we talk about exponential functions at all? We were talking about inverse functions, and so what's going on here? Well, inverse exponential functions, they are one-to-one functions, which we kind of skipped for this class, and that's okay. But they're one-to-one, and that means that they have inverse functions. But what are the inverse functions? So, the logarithmic function with base b for b strictly greater than 0 and b not equal to 1 for the same reasons, it is going to be the inverse of the exponential function. So it has to have the same suppositions on its base value. The logarithmic function with base b, or b greater than 0 and not equal to 1, is denoted f of x equals log and a subscript b of x, or y. So the way that's read is log base b of x. When you see that, like this is pronounced the way we say it in mathematics, we say log base b of x. And what that means is the logarithm with base b of a quantity x. And it's defined like this. So y equals log base b of x if and only if b to the y equals x. These two things mean the exact same thing. As long as the y value and the x value are correct, then this is two ways to say the same thing. So this is a new concept in mathematics that we haven't really seen before. This is something that we do a lot in mathematics called recursion. So recursion is defining something by something that you already know. And basically, a logarithmic function, you need to know what the exponential inverse would do. And that's how it kind of works. An exponential function, it takes an x value that's an exponent, and then it spits out a value. A logarithm is the inverse, so it undoes that. It takes in a value and spits out an exponent. Exponential function plugs in an exponent, gets out a number. Logarithm takes in a number, spits out an exponent. It does the opposite operation. This is a very common thing that you will see in your next math course. If you plan on taking Math 127, you will need to talk about inverse trig functions. And that is a very good, useful thing to think about. The exponential function, it takes in a value as an exponent and spits out a number, whereas a logarithm does the opposite of that. It takes in a number and then spits out the exponent needed. So that is how we define it. A logarithm and an exponential function are inverses of each other. And what that means is that log base b of b raised to the blue box is equal to the blue box. And b raised to the log base b of a green triangle is just equal to the green triangle. That's what that means. Now, I'm not going to draw it because this is our notes for it, but essentially when you do this in practice, the log base b and the b cancel. That's what's happening because they're inverse operations. Just like square rooting and squaring, those things undo each other. Logarithms and exponentials undo each other themselves well. So that's a very, very useful fact, and we are going to use that quite frequently in 2 sections from now. An interesting perspective to have on them is what we've already kind of talked about. An exponential function, the input is an exponent, the output is a number, whereas with a logarithmic function, the input is a number and the output is the exponent. And so you could be like Miss Arrington, my high school teacher who taught me this, and just try and beat the kids over the head with a ruler, with a meter stick until they figure it out, which is the way I had to learn it. It took me until being a TA in grad school that one of my students, Drew, still remember him from Math 1130, which was business algebra. He showed me this trick from his class, and I've used it ever since because it's a very, very good way to do things. So you have y equals log base b, right? And you want to convert this, log base b of x, and you want to convert this to exponential form. Or vice versa. You want to go from exponential form, which we just wrote above was b to the y is equal to x, right? That is the format. In either way, if you want to convert from logarithmic form to exponential form or vice versa, you always start with the base, move across the equal sign, and then back over to the last, to the other variable. So you'll see what I mean in just a second, once you've drawn it all out. Start with the base, move across the equal sign to the other variable, the other letter, and then back over to the other isolated letter. So the way it's working, it's in logarithmic form. To get an exponential form, it's b to the y is equal to x. And it works in reverse. Start with the base, work your way across the equal sign, and then back over to the last letter available. But now we're going from exponential form to logarithmic form, so we need a logarithm. Log base b of x is equal to y. So that's a memorizing tool that you can use, and it's great. Start with the base, across the equal sign, and then back over. We will be doing that a couple times to get practice with it. Anybody want me to show it again? It's okay if you do. All right. Oh, again? Yeah, for sure. So if you're going from logarithmic form to exponential form, you're going to no longer have a log in the title and in the statement, but you still start the equal sign, the base b to the y is equal to x, or vice versa. Log base b of x is equal to y. So that's how you can convert. And we'll do a couple times to practice it. There are some special bases, just like there was this special base for the e value. The natural base e is the most common one of the most common logarithms that exists. It's the natural logarithm. So it's called the natural logarithm, and it's denoted ln of x. So I know who has been coming to class versus those who don't by whether or not they write in in the program or they write ln in the program. Because if you're looking on ALEKS, it looks like an I, a capital I. The students think that it's in of x. ln of x. It's the natural log. And that's because writing log base e is too much work. That's the only reason I can think of as to why we do that. It's because, honestly, as you will see if you plan on taking calculus, the natural log is the most commonly used logarithm that we have. So we want a quick way to write it. We save ourselves 1, 2 pen strokes every time. And then base 10, this is one of the ones that's very, very common for us because we work in a base 10 system. Our number system is base 10. If we were if you've watched Project Hail Mary, I don't think they mention it in the movie, but in the book, Rocky works in base 32 or base 60, I can't remember. So probably if mathematics evolved in their culture, they probably their common logarithm would be base 60 instead of, or whatever their base counting system is, whereas ours is base 10. So it's called the common logarithm, and it's denoted log of x, no base. No base is listed. So it's the common log because it is one of the most common things that we use logarithms for. If you plan on taking astrology, astronomy. Astrology is the study of like the zodiac symbols, right? Yeah. So if you plan on taking astronomy or biology at some point, specifically natural biology, like a real life, population biology stuff, a lot of times you are studying things that are very, 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 very large, right? The moon is how many feet away? It's some obscene amount. And sometimes to try and measure the difference between things, trying to put that on a scale on an XY grid, it's too hard to read because like the distance from us to the moon is large, but from us to the sun is like 30 times that, like way more than that. And so sometimes we use what we call a logarithmic graph, and it allows us to take big numbers and convert them to exponents so that we can see all the data on one screen. So that is one of the reasons why we use this. One of the most common applications of logarithms is the Richter scale, which when I was teaching in Ohio, nobody knew what it was because they don't get earthquakes in Ohio. but most people here know what the Richter scale is. It's the way we measure the intensity of an earthquake. And because it's a logarithmic scale, it means that each one step up is 10 times more deadly. So a Richter scale of a 6.0 is 10 times more destructive than a 5.0. And so that's the reason why we have that scale. So like the Loma Prieta was like a 9.7. It's one of like the most devastating ones in American history. And it was very, very bad. So it's because it's based like that's very, very close to 10. So anyways, that is true. That's right. The decibel system, hence the name a decibel, deci meaning 10, is also a logarithmic system. Very, very good. So I've got this problem that is converting from logarithmic to exponential form. It seems like a silly tool that we'll have to memorize, but we will be using it a lot in 3.6, 3.5 and 3.6. So I'll do the first, I'll do A, B, and A, B, and G, and then we'll go for, and I'll have you guys fill in the rest. So the first one, it's given to us in logarithmic form, but no matter what form it's in, you always start at the base, work across the equal sign, and then back over. So to write this out in exponential form, it is 2 to the third power is equal to 8. That's how we convert it. Start with the base, work across the equal sign, then back over. In this fun little curly method. I called it Drew's curly method when I first started teaching. The next one, it's log of x equals 7. That log doesn't have a base, so this is the common log. Common log, which means base 10. So start with the base, work across the equal sign, and then back over. So what it's saying is that 10 to the 7th is equal to x. Exponential form should have an exponential function. Logarithmic form should have a logarithm. That's why it switches. And the base is always the same. This exponential form is base 10 because the base is 10. This logarithm is a common logarithm. It's base 10. That's how that works. The next one. So I want to skip down to G for us. And then I want you to fill in the rest of them. So G, we're given the exponential form. So you start at the base, across the equal sign, then back over. So I'm going to do an intermediate step. It's log base E of 5 is equal to 2t. And if you were to write this on an exam, I probably wouldn't mark you down. Or what I probably would do, not on the final, but on this upcoming exam, if you do need to do this and you write log base E instead, I'll probably mark off a point and say rewrite it correctly and I'll give you full credit back. Because remember, if it's log base E, that's the natural base. This is ln. So we need to write this as ln of 5 is equal to 2t. Start at the base, we're across the equal sign, and back over. So go ahead and fill in the rest of the chart. And be on the lookout for any different bases. So if it's the natural log or e, then that's going to be needing to become an e or a natural log. And if it has a 10 or a log base or a log, that means base 10. So go ahead and start filling it out. I'll slowly fill in details. I have the answer to all of them up here if you'd like to check your work, but if you're still working through it, continue to do so. We did everyone, but so I'll put it all the way up to C. So for C, the base, because it's in exponential form, the base is 8. So starting at the base, working way across the equal sign, that's log base 8 of 64 is equal to 2. The logarithm outputs the exponent. It takes in the number and spits out the exponent. The exponential function takes in the exponent and spits out the number. So it does the undoing of it. This next one, it's -5 equals natural log of y. Natural log of y is technically log base e. So starting with the base e, cross the equal sign. So e to the -5 is equal to the thing on the other side of the equal sign, the y. E to the -5 is equal to y. With e, the base is 1/4. So log base 1/4 of 6 is equal to x. F, this was a base 10 exponential function. So it's log base 10 of 7 equals w, but log base 10 is the common logarithm, so we need to rewrite that as log. The log of 7 is equal to w. We already did G, and then the last one is to showcase that it doesn't necessarily just need to be one singular thing on the inside or on the outside of an exponential or logarithmic equation. It can be multiple things, but we still start at the base, work our way across the equal sign. 6 to the -2 is equal to the thing that's left, the 3y plus 1. Any questions on that? Okay. So, as a useful exponent rule, one thing that we will use frequently in 3.5, it's that if a to the u equals a to the v, if b to the u equals b to the v, then u is equal to v. If you have two things that are equal to each other and have the exact same base, then the only thing that's possible is that the exponents are equal to each other. That's a fun little nifty fact about exponential functions. And we're going to use that here. Now, you have a calculator, and if you bought the calculator that I recommended, then your calculator can do all these without using it. Like you can just plug into your calculator log base 4 of 64, and it will give you the answer, which is 3. But because it will play a role for us in a little bit, let's assume that we don't have that capability. Let's assume we're on a desert island, or our phone is dead, and we are in the process of trying to disarm a bomb or something like that, and it requires us to know what log base 4 of 64 is without a calculator. Of course, I'm not your mom. You can definitely do this on your homework and on the exams. If I like, I don't really even ask this. Maybe the final exam will have this. In which case, go bananas with your calculator. But this is more as a setup of a skill that we're going to use later. So we don't necessarily know what this value is. Let's call it y. Then we can convert this to exponential form. 4 to the y is equal to 64. Four to the y is equal to 64. Now, is there a connection between 64 and 4? Do they have a common ancestor? And what I mean by that is there a common base? Is 64 a power of 4? Yes, it's 4 cubed. 64 is 4 to the third power. So what we have is 4 to the y equals 4 to the third, which means that y is equal to 3. But y is log base 4 of 64. That's one way to do it. And that's mainly meant to get us practice for something we're going to do later. So I didn't know what the value of log base 4 of 64 was, so I called it y. I then converted the logarithmic equation into exponential form. 4 to the y is equal to 64. I then was able to correctly notice that 64 is a power of 4. It is 4 cubed. So we have 4 to the y equals 4 to the third power. There is, by this little important exponent rule up above, if you have two things with the same bases, but with different exponents, and they're equal, then the exponents need to be equal. So that's why we get y is equal to 3, but y is log base 4 of 64. I'm going to give these ones for you to try on your own time. But this one will equal -2, and this one will equal 4, if memory serves, right? 10 to the fourth. No, 10 to, it's 5, I think. 10 to the, sorry, 5. The answer is 5. And then these last two. Log base 7 of 1. So we don't know what this is. Let's call this y. Then, by converting to exponential form, 7 to the y is equal to 1. What is the only value of y possible? 0, because anything raised to the 0 is equal to 1. Save for 0 to the 0, which is equal to 1 when it suits us. Oh, so itchy. But y is equal to 0. And in fact, this is going to be a true fact about any logarithm. Log base b of 1 is always equal to 0. And then natural log of 0. What is natural log of 0? You can use your calculator and it'll say math error. It'll say math error. This is a trick question. Because if we were to try and set this up, what we'd be saying is that e raised to the y is equal to 0. But this is impossible. Because e to the y is strictly positive. As we saw in the previous section, the range of all exponential functions is parentheses 0 to positive infinity. They are always positive, so they could never equal 0. So the answer is that this is does not exist. It's not even that it's not a real number. So like remember with square root of -4, the answer is not that it doesn't exist. It's just that it's not a real number. Here, it's just straight up does not exist. It's like trying to divide by 0. It's undefined. Complex numbers can go into logarithms if you're curious, but that requires complex analysis, which is something that is a 400 or plus, a 400 plus level math course. Very fun stuff though. Okay? But once again, you can use your calculator on these things. It's mainly meant to get us practice converting between logarithmic and exponential form. The graphs of logarithms. So because a logarithm is the inverse of an exponential function, and we learned from 3.1 in particular, a comma b is on the graph of A, graph on F, if and only if B comma A is on F inverse, right? The inverse function has the flip-flop points. So in that previous section, we saw that it had the y equals 2 to the x had the point negative 1 comma 1 half. That means that the logarithm has the point 1 half comma negative 1. And instead of the point 0, 1, it has the point 1, 0. And instead of the point 1, 2, it has the point 2 comma 1. So I'm going to graph the first function in blue and the second function in red. So the exponential function, as we saw before, has the point, has a horizontal asymptote at y equals 0. So this is f inverses f's HA. And it had the point negative 1 comma 1 half, 0 comma 1, and 1 comma 2, and it looks like this. But on the flip side, the exponential of the logarithmic function, it had x equals 1 half, y equals negative 1. So right there, it had 1 comma 0, and it had 2 comma 1. So this function, the logarithmic function, instead of having a horizontal asymptote, it ends up having a vertical asymptote. F inverses VA. And what a logarithm looks like this. And that makes sense because that's a mirror, that's a reflection across the line y equals x because they're inverses of each other. That's how it works. So exponential functions have a horizontal asymptote. Logarithmic functions have a vertical asymptote.
Is there a like a diagonal asymptote between the two functions?
Basically, there is a diagonal function y equals x that basically splits them, reflects them across that line. Good question. All right, so some properties about them. Their domain. The domain of a logarithm is parentheses 0 to positive infinity, and their range is negative infinity to positive infinity. It makes sense because of the properties of inverse functions. The domain of a function is the range of its inverse, and the range of a function is the domain of its inverse, and vice versa. So since the domain of a exponential function was negative infinity to positive infinity, the range of a logarithmic function is that. And since the range of the exponential function was 0 to positive infinity, that's the domain of the logarithm. This means this one also has a big point. This means with log base b of a red box, we need the red box to be strictly positive. I don't know why I changed color. It has the two important points. It has f of 1 is equal to 0 and f of b is equal to 1. So we have the points 1 comma 0 and b comma 1, and it has a vertical asymptote at x equals 0. Now, one thing that is interesting about these things is this is what they look like for different values of b. I can tell you though, from my own experience, I have never worked with a logarithmic function that has a base that is less than 1. I have very rarely ever seen that. I don't plan on putting that in any of the problems on the exam or on like I don't foresee them doing it on the final exam. If they're gonna put you, if they're gonna make you graph a logarithm, it's gonna be a logarithm with a base greater than 0 or greater than 1 because they never show up. They never do. Okay. How much do we have left? We have that. Okay. So one other thing that I want to mention as an important little concept to understand about logarithmic functions is that unlike exponential functions that grow very, very, very fast, logarithms grow very, 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 very slowly. It takes them a very long time to get to go to infinity. They do eventually reach infinity, but it takes a very, very long time. Case in point, if I do natural log of 100, just 100, right? That's 100 tick marks to the right. Natural log of 100 is 4.6. So it took us 100 tick marks to get a y value that's a little less than 5. Natural log of 10,000 is 11. So going from 100 to 10,000, so 990 more tick marks, we only go up an additional 6. If I make it 10,000, if I go to 100,000, sorry, 1 second. It goes up to 13. So it grows very, very slowly. As you get further and further out, it takes longer and longer to get up one more tick mark on the y-axis. They're very very, very slow growing functions. Basically, the slowest growing functions we know of. Okay, so let's go ahead and graph one of them. Y equals log base 5 of x plus 4 minus 2. Now you can follow transformations or you can plug them in. But I don't know if the ALEKS program has a button for log of 5 or log base 4 of the log base 5 of 4 or whatever. So these ones would be best done with transformations, unless it's a natural logarithm, in which case then you need to do something a little bit strange. And usually for those ones, I think it has the program where it shifts it left or right or up or down for you. So with this one, RCS, there is no reflections. There's no negative x, so we skip that step. There are actually no reflections. There are no compressions or stretches, but there is a shift down to and left 4 because it's x plus 4, which means we think we'd be going to the right, but we're actually going to the left because the horizontal stuff is always the opposite of what you'd think. Now the parent graph is y equals log base 5 of x. That has the point 1 comma 0 and 5 comma 1. So, and it has a vertical asymptote at x equals 0. And so the curve looks like this. So all we need to do is just transform those points, those 2 points, and it should graph the rest of it for us. So 1 comma 0 gets shifted down to 1, 2, and left 4. 1, 2, 3, 4 to the point -3 comma -2. And then we have the point 5 comma 1. It gets down 2 units, 1, 2, and then left 4 units, 1, 2, 3, 4 to the point 1 comma -1. What do you think happens to its vertical asymptote? If I move this graph up or down, the vertical asymptote doesn't change. But if I move it left or right, It does change. So it's going to move to the left 4 units. It's going to have a vertical asymptote at x equals -4. So let's graph that. And then let's plot those 2 points we had, -3, -2, and 1, -1. And then we have everything we need to graph it. It actually grows even slower than that, actually. If I wanted to be truthfully accurate, what I would have graphed in purple would be like this. It takes until it's 25, well, 21 in order for it to go past the x-axis. So, but either way. Okay. We got 2 other ones, and then we've got these other 2 problems and these 2 problems. So we are a little bit behind, but that's okay. I'm going to post pretty soon. I'll post a pre-lecture later today of to prep us for 3.4, and then we'll move on from there. Okay. That'll do it for today. If you have any questions, feel free to email me. Just as a final reminder, because a couple people came in late. So exam was originally scheduled for Monday of next week. It is being moved to Wednesday of next week. So it is not this coming Monday, but this coming Wednesday with the exam. If this affects your schedule in any way, shape, or form, feel free to come talk to me and we can see what we can set up, okay? Otherwise, have a great rest of your day, and I will see you guys on Wednesday.